That's it. So anyway, I'm going to talk tonight about stuff that I learned about while I was traveling this. I knew about them, but I became more interested in them while I was in Australia. I'm on my last year before I formally retire in the end of August, and but I hope to stay active in astronomy and research with various students and collaborators. There's actually going to be a conference for my retirement in Belgium this summer, which is kind of going to be fun in July. And but because I don't have to teach this last year, I got to travel, and I went to Australia to visit colleagues that I know there. And this is one of the things I got really interested in, these so-called tidal disruption events, things that happen when a black hole is sitting at the center of galaxies. Every galaxy, we think, has this, what we call a supermassive black hole that is much more massive than our sun or typical stars. These are million to billion times the mass of our sun, sitting in the middle of galaxies. We'll talk more about that in a minute. But there are stars that are orbiting around these black holes. And every once in a while, the stars interacting with each other, one of them gets deflected close to the black hole, so close that the black hole rips the star apart and make what we call a tidal disruption event. And this makes it really bright for about a year, for on the order of a month to a year, and up to 1 trillion times as bright as the sun. It is intrinsic brightness. And so now these are very rare. It only occur once every, I think they said 100,000 years in a given galaxy. But because we can now monitor the stars with these automated telescopes, we can monitor millions of stars. We can actually detect these rare events. This is something called time domain astronomy, the ability now to study stars and rare events that are varying in time. And because we can do this now, we know of over 100 of these tidal disruption events. So now this whole is very interactive, so if I say something that seems too bizarre to you or you don't understand, please interrupt, and so we're all friends here, okay? So because they're called tidal disruption events, I think the first thing we should do is try to understand what it is. What are tides? Where do tides come from? So of course, the most obvious example of tides is something we're all very familiar with. If anybody here live near the shore, and you know that twice a day there's a high tide and a low tide, what causes that? Well, it's primarily the influence of the moon, although the sun also has some role in the tides. But because the moon is so much closer, even though it's much less massive than the sun, the moon is the primary driver of tides. And when the sun and the moon are lined up, you get the strongest tides. And when the sun and the moon are at 90 degrees to each other, then they kind of compete. But the moon wins out. So, okay, so it's the gravity of the moon exerting its force on the Earth that causes the tides. So now how does that work exactly? Because gravity depends on how massive the object is, but also how far away it is. It depends, as Newton taught us, as the mass divided by the square of the distance. So you might think, well, the tides will depend on that 1 over distance squared. But we want to actually, the tides are actually what we call a difference effect, a differential effect. That is to say, if we look at the moon pulling on the Earth, and the Earth pulls on the moon, and they're in orbit around each other, but the moon's gravity is a little bit stronger on the side of the Earth that's facing the moon because it's a little bit closer than the center of the Earth. So in effect, any water that's on the surface of the Earth gets pulled towards the moon away from the center of the Earth and causes the tide to be high. So that's pretty obvious. The closer you are, you're going to get pulled towards the moon. But what's a little bit more puzzling at first is that there's also a high tide on the opposite side from where the moon is That is to say, if you think about high tide, the moon will be right above you, more or less. But it's also high tide when the moon is directly below you, you can't see it. And the reason for that is that the moon is pulling more on the Earth, on the center of the Earth, than the water that's on the far side of the Earth. So the net effect is to make the spherical Earth want to become more like an oval shape. Okay? Now, as the Earth turns, this bulge, this tidal bulge, tries to keep pointing at the moon. But as the water comes along and it's kind of, it runs into continents and other things. And so wherever it runs into continents, it plows up against the continents. And if the geography is just right, for example, in the Bay of Fundy, the water just gets pushed up the channel and you get 40-foot tides. I go up on Cape Cod where we get easily 10, 12-foot tides because of Cape Cod Bay smashing up against Massachusetts. But on the way back from Australia, I had the great fortune to meet my wife for a holiday in Tahiti. And there the tides were only about less than a foot because there aren't any big continents in the way to cause the tidal bulge to run up. So the tides are really not that big unless they run up against a big landmass. Okay, any questions about that? About tides? That's something we're all familiar with. Yeah, go ahead.
So at the poles then, will there never be tides?
Yeah, yeah, that's right, exactly. There's not much, there's the Arctic Ocean over there, and then you got Antarctica on the other side. But the tides are primarily, the moon orbits around, it orbits in the same plane as the Earth orbits around the sun. The Earth itself is tilted a little bit, so there's a bit of a change with the seasons about how strong the moon's tides are affected. But that's a very good question. Okay, so now let's talk about what happens if we push this effect to a limit. It's called the Roche limit, or the tidal disruption limit. So imagine you have a moon going around a planet, like we do it. Jupiter has dozens and dozens of moons, 4 big ones. Saturn has also a bunch of moons. But Saturn has, as we look in that picture over there, it has these rings. Why does it have rings? It's because if a moon tries to form, or if it gets pushed in too close to Saturn, or too close to the parent body, that moon will get ripped apart by the tides. And so this is called the Roche radius, or the tidal disruption radius. If the moon gets too close to the parent body, it can't actually. The gravity of the moon itself gets overwhelmed by the difference in the force between the front side of the moon and the back side of the moon, and so it gets ripped apart, and it makes a bunch of little rocks, and those rocks make the rings. So now I'm going to do a little bit of math here, but if you don't follow the details of that, no big deal. I just want to give you a little bit of background because this can actually be worked out quantitatively. You can go and look at this effect, and because the difference between the force in the front part and the back part of a moon, you take the difference of 1 over distance squared, it scales as 1 over distance cubed. And so then if you set those two things equal to each other and you solve for the radius at which the tidal disruption will occur, it scales as the radius of the moon times the ratio of the mass of the big object, namely the planet, over the mass of the moon, to the 1/3 power. That 1/3 comes from the fact that the tidal effect falls off as 1 over distance cubed. Okay? So this gives us a formula of how close we can get. And this is alternatively called the Roche radius, or the Roche limit, or it's also called the tidal disruption limit. Okay? All right. So that's why Saturn has rings. The Saturn's rings are inside the radius where this Roche radius. And so some body got too close, it just got torn apart. Or it couldn't form a moon at all. But there's another example. You might remember back in the 1990s, we observed a comet hitting Jupiter. And when that comet got close to Jupiter, before it actually impacted in its first pass, the tides of Jupiter actually ripped that comet into a bunch of little beads. These are actual pictures of a comet that had been torn apart by the tides of Jupiter on the first run, and then it came back and they all hit the planet the next time. Okay? That's pretty cool. All right, so that's all about tides. Now, what are black holes? Okay? Because we're going to talk about disruption of a star by a black hole. So the first thing we want to ask is, what is a black hole? Well, it's essentially when the escape speed from a body equals the speed of light. So you remember the astronauts when they flew to the moon in the big Saturn V? They had to propel themselves to a high enough speed to be able to reach the moon, essentially to escape the Earth and be captured by the moon. That speed was about 25,000 miles per hour. Or if you write it in terms of kilometers, which is what scientists like to do, and seconds, it's about 11 kilometers per second. Right now, the distance between us and, say, Wilmington is maybe about 20 kilometers, I don't know, something like that. So it takes 2 seconds for escape speed. If you could travel at a speed that would take you 2 seconds to get to Wilmington and put that speed upward, you would never come back down. So like, for example, let's take one of these little things here. If I take this thing and I throw it up in the air, it comes back down. If I throw it up even faster, it comes back down, it goes a little bit higher. If I continue to make it go faster and faster and faster, there'll some point where it gets so far away from the Earth that the Earth's gravity weakens and it never stops. That's called the escape speed. And scientifically, it can be written in this formula. It's the square root of a constant that Newton introduced, which is telling you how strong gravity is, times the mass of the body divided by its radius. The square root of that quantity, that gives you the escape speed. So now, the escape speed from the Earth is about 11 kilometers per second, or 25,000 miles per hour. The escape speed from a surface of a star like our sun is much more. It's 615 kilometers per second. So it's like 60 times, roughly, the escape speed from the Earth. The sun has much more mass, and therefore has much more gravity. It's bigger, too, but it turns out that the ratio of these two things makes it bigger. Okay, so now a black hole is when you make the escape speed equal to the speed of light. Because nothing can go faster than the speed of light. So in a black hole, light can't escape from it. That's why it's black, right? And so I just took a couple of examples. If you had a black hole, if you took the mass of the sun and squished it down to only 3 kilometers in radius, or 6 kilometers in diameter. Here's 6 kilometers in the map of Newark. You know, it's about the size of the city of Newark, right? If you made the sun the size of Newark, it would be a black hole. Light would not be, to escape from it, it would be a black hole. So in other words, anything can be a black hole. Even the Earth could be a black hole. But in order to make the Earth a black hole, you have to make it the size of a marble. You'd have to take all of the mass of the Earth and make it the size of a marble. Now you can also work out how small would you have to make us a black hole, and it's like, you know, tiny, tiny scale, the size of an atom or something like that. If we take our mass and compress it down. So anyway, the point is that black holes don't have to be very massive. They can just be any mass, but you have to compress it down to make the gravity so strong that not even light can escape. Okay? So that's what a black hole is. Anybody have any questions at this point? Okay, so what happens to stars when they die? Well, a star like our sun will become something we call a white dwarf. It's held up by electrons bumping up into each other. And it'll be about the size of the Earth. The sun will get compressed to about the size of the Earth. But that's not small enough to make it a black hole. If you take a star that's a little bit more massive than our sun, the electrons will not be able to hold it back, and it will compress and become a bunch of neutrons. We call that a neutron star. And those are typically maybe 20 kilometers. For the sun, it would be about 20 kilometers in size. But then if you make a star that's very, very massive, when it finally dies, it cannot even, neutrons cannot even keep it from collapsing even more, and that's called a black hole. And we know about many black holes that happen to be in orbit. How can you observe a black hole? It's black. Well, one of the ways you can observe it, if you spill stuff onto it, then the matter that's falling onto the black hole gains a lot of energy. It's like if I drop this thing or anything, and I drop it on the floor, it gains energy by the gravity. Well, the stuff that's falling onto a black hole gains so much energy, it becomes really, really hot. So if you can have a source of matter to fall onto the black hole, it'll shine very brightly. And so this is an example where two stars were orbiting around each other in a binary system. One of the stars was very massive, it exploded and left behind a black hole. Then the other star, as it got older, it bloated up and it tries to spill matter onto the black hole. Now the matter can't directly go down to the black hole, because just like when you let water out of your bathtub, unless you make it really still, what happens? The water doesn't go directly down the drain, it swirls around. And that's what happens. We call this an accretion disk, because the material that's coming from the other star has too much rotational motion, too much angular momentum. And so it has to get rid of that angular momentum through what we call an accretion disk. But ultimately, that material, as it falls into the black hole and gets closer and closer, it gains more and more energy, and it gets hotter and hotter and hotter, and it starts to shine. And we see these kinds of events in X-rays and gamma rays and things like that. So, so the upshot here is that you can see black holes if you dump matter onto them, or you can see the effect of them. You can't actually see the matter that falls into the black hole, but you can see the effect of the energy that the matter gains. Okay, so this is called an accretion disk. This has been known for a long, long time. We have many examples of stars where there's a black hole that might be a few times the mass of the sun around another star that might be 10 or 20 times the mass of the sun, and they get so close that they spill matter onto each other, the star spills matter onto the black hole, and then as it does, it shines. And it also, at the last minute, it shoots these huge jets out, and we can see the effects of those jets too. Okay, so this is the kind of process that people had known about for many, many years. Black holes of masses a few times the mass of our sun that are getting matter falling onto them. Okay, but now we're going to find out that there's another kind of black hole, what's called the supermassive black hole, that are at the centers of galaxies, including our own Milky Way. So this is an actual photograph of stars at the very center of our galaxy. And if you remember, when you look in the sky, things are measured in angular size. So for example, 1 degree would be 1/360th of a circle. But then you can break that degree up into 60 minutes, and then you break up the minute into 60 arc seconds. And so this angular size here is 0.12 arc seconds. Now you have to have a really good telescope with really special properties to be able to see angles that small. But nowadays we have these top telescopes which have what's called adaptive optics, which correct for the turbulence that the Earth's atmosphere is always trying to make and blur images. And with this telescope you can get resolutions down to 1/10 of an arc second. Otherwise, seeing this weather effect, this atmospheric effect, will always blur the images to 10 times that, and then you wouldn't be able to see these stars. But there's a telescope called the Keck telescope that's part of the UCL, University of California, Los Angeles. Andrea Gates, who is the leader of this group, won the Nobel Prize for the observations that I'm about to show you just a few years ago. And so let's see if we can make this go here. Oh, come on. No, come on. Oh dear, let's see. How do I get this to turn on without, nope. I might have to, well, I didn't anticipate this problem. Just a second. Nope.
What if you click on the image?
I tried clicking on the image. Click on the actual image up here.
Right.
If I can get up there. See, I don't think it lets me up there. So I'm going to have to do escape here. I think it's going to screw up my recording. But say let me show navigator. Yeah. Yeah.
Maybe one of these icons will get you into a different viewing mode. So maybe you'll be able to.
There it is.
Oh, here you go.
There we go. Okay, so this is actual real data. This is real observations over many years of how the stars at the center of our galaxy are moving around. They actually watch them move in the sky by this small amount. But you notice they all move in oval shapes around that central phenomenological star. You know, there's nothing that's visible there, but all these stars are moving around it. Let's see if I can do this again. What did you think right here? There it goes. So watch this guy, for example. I think they call this one SO2 or something like that. That one actually made an orbit. It took about 15 years for it to go around. And then it starts to repeat itself. And then this guy kind of turned around on a dime and turned around. There has to be something very, very massive there to cause stars to just turn around on a dime. These stars are 10 or 20 times the mass of our sun.
And I noticed in the image, like the way that it got closer to the center, it went faster.
Went faster because
And then it
when you
goes
get,
slower.
just like if you're on a roller coaster and you go down, you go real fast.
Right.
And when you come back up, you go slower again. That's the laws that Kepler and Newton taught us about orbital motion. But then Kepler gave us this beautiful set of relations that tell you if you know the period it takes to make an orbit, and you know the size of what's called the semi-major axis, the half size of that oval, those two things tell you what the mass is at the center that's causing it to orbit. So you can just use Kepler's laws to work out what the mass is of this object that we can't see. And it turns out to be 4 million times the mass of our sun. 4 million times the mass of our sun. Now, you may have heard that there's this new thing called the Event Horizon Telescope. The Event Horizon Telescope looks at, even though there's not much visible observations, emission from this area around the black hole, there is emission in the radio, and by using different mirrors spread all around different radio telescopes spread all around the Earth, they can combine the image and actually image the radio light that's coming from the center of our galaxy. And this is a famous result of the Event Horizon Telescope, it's called. It's basically a picture of the black hole at the center of our galaxy taken in radio light. And the size of that, what's happening really is the light's just getting bent by the gravity, and it forms this beautiful image. And if you look at the black part, that has a diameter of about 12 million kilometers. And I forgot to mention this, but we did actually mention it, that a black hole the size of our sun is 3 kilometers. So the fact that this is 12 million means that this thing has to be 12 million divided by 3, or 4 million solar masses. But it's also known from the orbital motion, but those two things are consistent. Okay, that's the center of our galaxy. Yes, sir?
What is the color scale?
Oh, this is it's using it to kind of show a range of brightness.
Just brightness.
Yeah, it's mostly just brightness, yeah. Okay, anybody else?
Why is it asymmetrical?
Well, that's a good question. Partly the reason is that whatever material there is not symmetrical, and it's also tilted. It's probably in a disk of some sort, and it's tilted to our line of sight, so you tend to see foreshadowing brightness on one side. Okay? All right. So that's really cool. But before this image was made, the Event Horizon Telescope made an image with the same technique of something that was 1,000 times, more than 1,000 times further away. And they saw this. Now that image is 1,000 times further away. On the sky, it has roughly the same angular diameter. That must mean that it has like more than 1,000 times more mass. So instead of 4 million solar masses, it's more than 4 billion solar masses. 4 billion with a B, right? I mean, the mass of this black hole is estimated at about 6.5 billion suns. That's about the number of people on the planet of Earth. 6, 7 billion, 8 billion people. So this has as much more mass than the sun as there are number of people on the planet Earth. Okay? Now, this can also be looked at, like here's the image. Then it turns out if you use polarization, you can see that the light that's coming from this black hole is actually polarized. And that's because there's magnetic fields threading the material as it falls into the black hole. And then it turns out that if you step away, you find that this black hole has a huge jet coming from it. And that jet is coming from matter as it falls into the black hole, it makes that jet. Just as we showed in that accretion picture, that there was a jet.
I have a question there.
Yeah.
So how does the jet escape the gravity?
Well, it's just fairly powerfully accelerated by processes that are related to the tangling up of magnetic fields. There's something, well, it's a very, it's not an easy thing to explain, but it involves the magnetic torquing of material as it falls in, and then it gets something called a hoop stress. And it seems that everything that has accretion often has a jet. We find that at all different scales.
Got it. So it does fall into
The material, some material, a lot of material falls in and a little bit gets shot out. It's kind of like it's like maybe if you have, try to compress something and you get a little squirt out the side. Some of it gets contained, but a little bit of it squirts out. Okay, so now let's go back to talking about tides. Because now the black hole has really, really intense gravity. Okay? And so people say that if you follow into a black hole, you're not going to make it because the tidal effects that we were just talking about that rips apart moons and makes rings around Saturn would make a human being who tries to go into a black hole spread out, stretch out, and we call a process which has been given the name spaghettification because it turns anything into this long, thin spaghetti thing. And the way you can understand that is, imagine you have 4 different dots here that are objects falling into a black hole. And they're in a perfect square or diamond. But then the gravity is strongest on the one that's closest and weakest on the one that's furthest. And so after a certain amount of time, that triangle gets stretched, just as we were talking about before. And so that when you get near a black hole, that stretching becomes so intense that nothing could really survive, even at the tidal. The difference between the gravity at my toes versus my head would be so strong it would pull my body right apart. Okay, so that kind of tells you that if you get too close to a black hole, it's really tough. So here's the process of a tidal disruption event. You got all these stars buzzing around this black hole. It's like we saw in that movie. But there are thousands and even millions of them buzzing around. And every once in a while, 2 of these stars get close enough that they actually deflect each other. And on some probability that sometimes the outcome of that deflection is to send one of those stars almost right at the black hole. So close that it gets within the so-called tidal disruption radius. So there's the tidal disruption radius. There's the formula that we learned earlier. Only now, instead of the mass of the planet over the mass of the moon, we have mass of the black hole over the mass of the star to the 1/3 power. And then we have this formula. So if if a star comes in, as it gets closer and closer, it starts to get stretched. But when it gets this place, some material that's inside of the tidal disruption radius gets trapped in an orbit around the star, and other material gets flung out like this. And that's the kind of event that happens near a black hole. Now, remember we said that the black hole, here's a radius that scales with the 1/3 power of the black hole. But remember we said that the radius of a black hole itself scales linearly with the mass of a black hole. So if you make the black hole big enough, the black hole radius is going to be bigger than this tidal disruption radius. So if you make a black hole too big, and this turns out to be about 100 million solar masses, a star like our sun would not get disrupted. It couldn't get close enough. It would just fall directly into the black hole. And so these tidal disruption events are coming from black holes that are kind of like the one in our galaxy, as opposed to these one in M87, which was 6.5 billion. Okay, that couldn't make a tidal disruption event. It's too big. It's too big. It has too much mass. So the black holes that are making tidal disruption events are of the order of 1 million suns. And they just take stars, they get too close to them, and they rip them apart. So, okay, go ahead.
Do black holes evolve, so do they start small and continue to grow?
They can, if they keep getting matter added to them, they get more and more massive. Now, it used to be thought that if you just left a black hole alone, it was black, it was never going to, it would just sit there forever. And there was this guy, you probably heard of him, Stephen Hawking, who realized that no, black holes they give off what's called radiation, a small amount of radiation. And then eventually the black hole will evaporate by just giving off light, giving off some radiation. But it turns out the time it takes for a solar mass black hole to do that is 10 to the 50th, let's put it this way, it's 20 orders of magnitude longer than the age of the universe. Okay, so it's not going to happen in our universe. But it does, in principle, black holes can evaporate eventually. But most black holes are accreting matter from just material around them or from the interstellar medium, so they're gaining some mass. And if they do, whenever matter falls into the black hole, it gets very hot and will radiate until it actually gets captured.
Back to your spaghetti illustration,
Yep.
right? So is there a galaxy black hole, coupling that has evolved to the point where there's just no stars around the black hole anymore?
No, because you got to really be the rare guy that gets too close. All these other guys are buzzing around very far away from the black hole, and they're just like with the stars that we saw. They're just going around the black hole, and they don't get hurt at all by the black hole.
That's what I mean. So a galaxy where all of the stars that were close enough have already been consumed.
Yes, and as a matter of fact, for galaxies that had enough disruption so that they had lots of stars feeding them, they become what we call quasars. Because they have so many stars being disrupted all the time, this material in their accretion disk, they just shine like crazy before. And that happened a lot in the early universe, when the universe was much denser and galaxies were colliding a lot with each other. And the collisions of the galaxies send all the stars in crazy orbits, and some of them get too close to the black hole and they get caught in this accretion disk, and then they just power. And so the events that I'm talking about are for black holes that are kind of quiet and otherwise not like ours, the center of our galaxy. It's not really emitting very much radiation. But if a star got too close, it could disrupt it, and then during that time, it'll give off more light than the rest of the whole galaxy for a short amount of time, for a year or so. Anyway, yeah, good question. In some galaxies, there's enough of this feeding going on that the thing just becomes what we call a quasar. It's just giving off a tremendous amount of light all the time. Good question.
I think, yeah, Ghosh, I think
Did
so.
you have a question?
Yeah. So you were saying galaxies cannot exist without a black hole in the center?
Well, nobody knows for sure, but we find empirically that every big galaxy we look at has a black hole in the middle, and that the mass of the galaxy is proportional to the mass of the black hole. It's almost like the acorn that makes an oak tree. It's very, very small compared to the oak tree, but it's the seed. So a lot of people think that galaxies formed around these black holes and that it plays a big
Keeps
role,
it together.
plays a big role in galaxy formation. Very good questions. Okay, so we're back to this. This is an animation. Let's see if I can get this to work now. What did I have to do? This one? Nope. I don't know where that came from. Let me just pardon my incompetence when it comes to stuff like this. There it goes. Okay, this is a NASA animation of a tidal disruption event. That's a star, and it's orbiting around, and there's the black hole, and it gets close to the black hole, and it gets ripped apart, and then as some of the material escapes, the rest of the material goes into an orbit around the black hole, and then it kind of just becomes a cloud around the black hole. Okay? And I think this one is, I don't know if this will work or not. I think you have to have the internet for this to see if that works. Nope, it doesn't work. Okay, we'll just skip past that. Maybe at the end if anybody wants to see another animation. All right, so here's the basic scenario that when a tidal disruption event occurs, you get this jet that probably emits, in like X-rays and in the radio. You get material that's outflowing, and that can be observed in the ultraviolet and the optical, and then also near the equator. So as you look more towards the equator, you see light that has been processed. So let's use this as an example. When the sun has energy coming, ultimately, the thing that powers the sun is nuclear fusion in the core. And that's occurring at a temperature of about 15 million Kelvin. Surface of the sun is only about 6,000 Kelvin. The energy that's being created, the radiation that's being created in the center of the sun is very, very energetic. It's very hard. It's like X-rays and gamma rays. But now it can't just get out of the sun because it's got all this material around it. So it just bounces around, and as it does, it slowly becomes degraded and to the point it becomes visible light that we see from the surface. So whenever you shroud a source of energy that's very high energy around with a very opaque thing, it comes out, instead of coming out as gamma rays and X-rays, it comes out as optical. So ultimately, you see a lot of optical and ultraviolet light that you would see from a normal star from such tidal disruption events. And when you look at that, this is called the reprocessing of all the radiation. You get signatures of things. There's the ultraviolet spectrum on the upper left, and there's these bumps of emission, and that's coming from material that's trying to flow away from the star. And some of that's just because maybe some of it got ejected out, but some of it is because the tidal disruption event is so luminous that the light itself is pushing material away from the star. And that's why I got interested in this, because I've spent my whole life studying hot stars that have this kind of outflow driven by radiation. So now I say, oh, this looks a lot like a very ginormous star. It has a luminosity of 10 to the 10 and 10 billion suns, so it's more luminous than anything we have. It's bigger, but a lot of the physics is the same. So here, let's look at some of the variations of light as a function of time from various objects. There are about over 100 of these tidal disruption events been observed now, because we have these robotic telescopes. This those things, that's A, that comes from a project called Assassin, which is basically designed to use small telescopes to monitor a huge number of stars. And they've discovered these over 100 tidal disruption events now. And this is how much light that comes from them, or when you take into account their distance, how much energy is coming from them per unit time as a function of time since the eruption. And what you can see here, this is in units of luminosity compared to luminosity of the sun. And this is in ergs per second, which I've converted for you to luminosity of the sun because it makes a lot more sense. But here's 100 million times. Well, they're all much more luminous than 100 million suns. And there's some up there that are a trillion. 10 to the 12 is a trillion, right? 10 to the 3 is 1,000. 1,000 is a million. That's 10 to the 6. 10 to the 9 is a billion. 10 to the 12 is a trillion. This object, these couple of those objects were a trillion times more luminous than the sun for a week or two, and then they fade. But by studying this, you can actually learn about what the objects were. Yes, sir?
So in terms of the shape of those light curves, you can determine what the object was, the class of the star that went into it.
Basically, that's it. And in fact, you just anticipated my next slide, which is showing you that the bigger the black hole that you fall on, the longer it takes for this phenomena to, so you can fit this light curve and get the mass of the black hole that you're accreting onto. Very great. I didn't plant him, I promise you.
Yeah, no, I was gonna ask what the relationship is.
Okay? Well, it's a little more complicated than this graph just shows the result, but the relationship is a little more complicated, but that's basically what happens. The bigger the black hole, the longer it takes for this event to unfold. And so we have black holes that are only 100,000 times the mass of the sun, 1 million, 10 million, 100 million. It doesn't go any higher than that, because any black hole that's more than 100 million will have its gravitational radius outside of the tidal disruption rate will be inside the black hole, and therefore you don't get any tidal disruption. Okay?
Is there fusion going on in the accretion?
No, there could be, but it's a minor contribution. So one of the things that's really cool, you've all heard of Einstein's formula, E equals mc squared, right? What that tells you is that you can get mass and you can turn it into a lot of energy. So the hydrogen bomb, for example, or the bombs, that just takes a little bit of the mass when you either split apart atoms or fuse them together to get energy. So it turns out the fusion that's powering the sun, if you take 2 protons and it's actually 4 protons and merge them into a helium nucleus, you lose about 0.7% of the mass, and that becomes the energy that powers the sun. But when you drop material onto a black hole, you get something like 25% of the rest mass. So in other words, fusion is really inefficient compared to the energy you gain by falling onto a black hole. You almost, black holes, if we had a black hole here, it could be our power source for the rest of the world, because all you'd have to do is drop a little bit of matter in it, and it would just generate huge amounts of energy. So black hole accretion is much more efficient than even fusion, and therefore if fusion's going on, it's just a minor process. Good question. Okay, so I'm going to finish up with just showing you the paper. This guy, Daniel Price in the middle here, and Ilya Mandel. Ilya Mandel was my host. He actually paid for my trip to Australia. And Daniel Price is a person who's an expert on developing the simulations of going on. And then Mr. Fanyi Hu is his graduate student. Anyway, they wrote this paper in which they did simulations of material falling onto the black hole, and and one of the things they found is that just a lot of stuff got stuck around the black hole, and it basically reprocessed the high energy from the central star. And so they have a whole bunch of simulations here. And so I've been studying this paper and trying to see if, what kind of input I can give them from my background. And that's we're starting a collaboration, basically. But this is the basic result, that when, the black hole is just at the center there, but this is how much matter is sort of surrounding this black hole. And it's basically opaque. And it's so opaque that all the energy that's being generated by falling onto the black hole is being reprocessed into optical and ultraviolet light. And so that's my goal, is to sort of study how that, here's, for example, synthetic light curves from these models. And I won't go through the spaghetti diagrams, but so when I was in Australia, I was at this meeting called the ANITA, Australian National Institute for Theoretical Astrophysics. And I had a talk, invited talk, and I just learned a lot about these tidal disruption events, and I decided what I know about, which is how light can drive away mass from a star I would see if I could apply this to these tidal disruption events. And that's basically where we stand right now. I hope to go back to Australia next our winter, their summer, and continue this research with them. So I'm going to end with just a little kind of a, I'm a scientist, but I also believe that science is philosophically a very powerful thing. And so when I teach my classes, I always try to illustrate some of the physics by using poetry. So I wrote this one poem called Black Holes. Now, I won't read the whole thing right now. I'll just read the yellow part. But I actually brought a bunch of little slips of paper that basically have the whole poem. So I'll pass those out in just a second. But let's just read let's skip the white part and just go to the yellow part, and then we can go back and read the rest of it if you want. So remember it said, it's talking about black holes, and then it's referring to their tides. So its tides are so heady that nearby space stretches and pulls to spaghetti all that it catches. Remember the spaghettification. Any star that is near gets sucked from its main, and with rotating shear, just falls down the drain. The energy gained makes falling stuff bright before it is chained and drops out of sight or falls out of sight. So watch from afar the fireworks that start when a hole near a star pulls it nearly apart. From Earth you are safe to watch the big show, not your body to chafe, but your young mind to blow. Okay? All right, well, that's what I had to say, but I just want to do a little bit of shameless plug here. I teach a course called Fundamentals of Astrophysics. If anybody's interested, this book is available online through Amazon. You can get it for about $35 on Amazon. It uses calculus, so it does use some math, but it's very descriptive. The person who reviewed it for Physics Today said you can take this book to a coffee shop and read it. And I think Jared can probably tell you that it's written in as straightforward a language as you can have, but it does have some math in it, but you can always skip past the equations and just learn about. And it covers everything from stellar properties, stellar structure and evolution, how stars evolve and how they work, the interstellar medium and the planet formation of stars and planets, then the Milky Way galaxy and other galaxies, and then the fact that all these galaxies are flying away from each other is how we know there was a Big Bang, and that's what we call cosmology. That's all covered in one semester. And Gary can tell you it's a lot like drinking out of a fire hose for the students. But there's a lot there. And if you want to follow up and learn some other astronomy that's a little more quantitative, there it is. And then the other thing I want to do...
Front cover.
I'm sorry?
It's got a good front
And it's got a good front cover. So this has the shows from the smallest scale, which is called the Planck length, up to the increasing scales to the size of a nucleus, to the atom, to a cell, to humans, to Earth, to Jupiter, Sun, the orbit of planets, and then eventually galaxies, and then finally the Big Bang. This is the results with the microwave background. Yeah, I was really proud of the cover. I didn't do the cover. I just gave the guy, the artist, a suggestion about doing it in a spiral, and it came out very nice. And then I also am a grandfather, so I've written a couple of children's books and also a couple of books. And I happen to have a couple of copies. I had one copy of each book here if anybody wants to just take a look at it. And unfortunately, these aren't published by a publisher, self-published right now. But if anybody knows a way, I've been trying to find people that can get me in touch with publishers that I don't have to pay thousands of dollars to publish. Anyway, this book is called Big Stars for Little Star. It's my first book that I wrote. It was based on a suggestion by my daughter-in-law to write a book for my first granddaughter. So she's the little star. The big stars are about what I study. Then my second granddaughter, my daughter, asked me to write a book for her, and I've been teaching about the scales of the universe, and it turns out the number of powers of 10 between us and the size of the Big Bang of the universe is about 26. So this little girl asks her grandpa, what's the biggest thing there is? And he says, well, I can't explain it to you, but I can show you with these magic jelly beans. They'll make you 10 times bigger, each one. So after 26 jelly beans, she's as big as the universe. And then these are 2 books that I've written for my classes. One is about the Earth, and one is about the sun. So if you go ahead and want to take a picture of that, you can find out how to get it and download them from those URLs. But I also have hard copies if anybody's interested. All right, well, thank you very much for your attention. It was wonderful to have this chance to talk to you. And I'll take any more questions if you have them. And let me shut off the recording. Okay, so, all right. So a lot of things in astronomy are balls, right? So I often start off these poems with, this is a ball, okay? So this is a ball that's way past its prime. Its core is a wall that nothing can climb. This ball is so massive that its gravity bends all that's passive to within its own ends. This even means light, which just can't escape. So it's black as a night with a negative shape, kind of like an inverted sphere. But light is our measure of our space and our time. It gives us all pleasure for all that's sublime. In the bend of light's sword, thus gravity makes both space and time curve until it then breaks. This break in space-time is called a black hole. It doesn't just waste time, it rips out its soul. So seen from the outside, falling clocks would just stop. But to one on the inside, they just fall in a pop. And the rest of it is its tides are so heady, like we just did before, okay? But here what it's telling you is that gravity actually warps not only space, but time itself. And so when material falls, when a clock falls into a black hole, we see it stopping. But to the clock itself, it just falls in a pop, it just falls in. So gravity is this weird thing that warps space and time. And that's the crazy thing about it. And when it finally is so strong that it breaks space-time, that's how you get a black hole. And we think there are